not to the, oh no, wrong button. Okay, never mind. All right, let me share my screen. So the goal today is to bring everything in the last week and a half into focus. So I'm pretty much going to touch on everything that was covered in all the other recorded lectures and hopefully make it a little clearer as to where things come from. And what I'm going to start with is just the general equation of motion for oscillatory behavior. So that's a position function. This x equals a is the amplitude, cosine omega t plus phi. The piece I'm not going to focus on today is this phase shift. Because all that phase shift does for us is say, if I don't start off at precisely 1 or 0, so a max amplitude or 0, that phase shift moves everything to where I can predict from time 0 what's going to be at any time t after. So it's not a big deal, but for today, we're just going to focus on how do we get from this basic sinusoidal function to like figuring out frequencies and amplitudes and displacements and all that. So to start with, in first quarter, when we started with motion, I threw these 3 graphs up on the board, and I said, these are useful for kind of deciding, do I need to take a derivative or do I need to take an integral? And what do each of those steps get me from a given function? So looking at the slope of the line, starting with my x, what are the units going to be for the slope of the line for x versus t, for position versus time? Just to remind everybody, slope is going to be the change in x, or rise over run. Let's just write it that way, more generic. Rise over run. So what units do we get for the slope for position versus time?
It's just meters, right?
Meters per second.
Meters per second, yeah. So you just forgot the time part. So that's my x-axis. So this is meters per second, otherwise known as velocity. And velocity versus time, what units do I have for the slope there?
Meters per second squared.
Beautiful. Otherwise known as acceleration. So when I'm looking at the slope, is that an integral or derivative?
It's a derivative.
Good. So slope is my derivative. Or you can think of it as just how much something is changing per unit time. So that's all a derivative does for us. So I look at this and then I say, okay, so if I look at the derivative with respect to position over some amount of time, that gives me velocity. So if I go dx dt of this a cosine omega t, what do I get from that? How do I take the derivative of this thing?
The derivative of cosine is negative sine, so it's chain rule, and you get negative a omega sine of omega t.
A omega sine of omega t. Perfect. Now, for those of you that didn't instantly remember, and some of us still to this day have to do this to remember which one is positive and which one is negative. So remember, the derivative is giving us the slope. And a cosine function starts off at 1. So the slope of the line is negative. So the slope of a cosine function is a sine function, and in the negative direction, it's a negative slope. Whereas sine starts at 0 and goes up. So its derivative is positive and it's described by a cosine function. Cool. Now, what if I take the second derivative of a cosine omega t? What do I get?
You should get negative a omega squared cosine of omega t.
Good. Cosine of omega t. Cool. Let's remind ourselves that this here then would be acceleration, and this thing here would be velocity. So if I know my amplitude and I know my omega, at any time t, I can solve, or actually, I wouldn't need to know my amplitude. If I knew omega, I can solve for amplitude. I can solve for what we call the phase velocity of this thing, which is what you get from that. Or I can solve for the acceleration. That's nice. The one thing I didn't do for you just now, and just in case, for those that are feeling rusty on derivatives, it is the derivative of the outside times the derivative of the inside. So derivative of cosine gives us negative sine. Derivative of the inside with respect to t, well, t raised to the 1 just makes the t go away, because it'll be 1 minus 1, so t to the 0 makes it 1, so the omega is the thing that pops out. And there we go, there's our omega. Cool. So I have that, and let's see, what else do I know? For this spring thing, what force is making, if I'm on a smooth, frictionless surface where air resistance isn't a big deal, what force is making that mass oscillate back and forth?
Okay, spring force.
Good, good. And that would be like negative kx, right? Is everybody good with that? Is there, I don't know, a net force here? Peter? For the mass oscillating back and forth on the spring, is there a net force there?
There's a net force of 0.
Is there?
Oh,
What would
sorry.
be-
In the y direction, there's a net force of 0. In the x direction, there should be a non-zero net force,
Good, good. And how do I know that?
because the block is moving in one direction or another, or rather accelerating in one direction.
Oh, so
Sorry.
more than that, just remind ourselves that if I have just a force going in one direction or the other, just like was just said, then that means I have an acceleration. Because the only way I have a net force of 0 would be if I had some other force equal and opposite going like that. So if I don't have another force, then that means that I have most definitely a net force. So I have F net, and what does F net equal, just in general terms?
ma.
Yeah,
Perfect.
Also,
So,
you
I'm
don't
sorry?
have enough force when it's at x equals 0, though, right? Your net force is 0 when x is equal to 0.
Yeah, but you
Oh,
have
sure.
then momentum kind of carrying everything through.
And then that's only for a split second.
Yep,
Cool.
yep. So let's see, my force net then is my negative kx. And that means I have mass times acceleration. So the other thing I can do here is then solve that acceleration is this negative kx over m. And let's see, I defined x up above. I said that x is a cosine omega t. So then I feel like I can rewrite a to say that a then equals negative k over m times a cosine omega t. Cool. So I have acceleration here and acceleration here. So I feel like I can set those two things equal to each other. Does anybody disagree with that? Okay. let me go ahead and do that. So then I'm going to get negative K over M A cosine omega t equals negative A omega squared cosine omega t. Ooh, this is getting exciting because I feel like cosine cancels with cosine, the negative cancels, A cancels. And so what am I left with? I get K over M equals omega squared, or my omega is the square root of K over M. That's what you're doing in lab this week. So you're looking at something oscillating vertically or horizontally. And we're looking at, relating period and frequency to that oscillation. So remember K, let's look at those units there. K is what has units of newtons per meter. And in Newton, well, let's see, that's mass times acceleration. So kilograms, meters. Oops. Helps if I actually write out the right thing. So I have kilograms times meters over seconds squared times meters. So that cancels. So my K, what did I just do? Newtons per meter. Okay, I'm doing something wrong with my units here. That should not have gone away. So I have, let's see. Oh, good, because M is mass. No, we're good. We're good. I'm done panicking. So kilograms over seconds squared, that survives from the K. And then what do I have here? I have over M, which is mass. So that cancels, and I do indeed, square root of 1 over S squared gives me 1 over S radians per second. So I have the correct units from that, which is neat. Any questions on how we got there? Do you see how we can kind of lay these pieces in and relate it to the things that we've done in the past? Because I'm going to have you apply it now. Okay. There's no questions. What I'm going to have you do, yeah.
Really quickly.
Yeah.
So you're messing with the K constant. That's the same thing. So K is also equal to omega squared times M.
Uh-huh.
And you end up with the same units by messing around with that.
Yep.
Cool. Okay.
It kind of hurts the brain sometimes.
Well, no, actually, that makes it a lot easier. At least it's consistent.
Yes. Yeah. Okay. So what I want you to do, and great question, thank you, is in your breakout rooms, we're going to look at this in terms of torque. So this thing is the typical first pendulum that we introduce you to. And it's this weird looking like bar that swings back and forth. And then we tell you that just pretend that that is a frictionless connection and it's just going to keep swinging indefinitely. We're not adding in damping yet, which would definitely exist in this system. And the reason why we're going to do that is we're going to do this pendulum and then the idealized pendulum, which has then a massless bar and then a blob at the bottom. And what we're going to do is connect those two behaviors to see that the generic definition, we're going to kind of go through these same steps that we did up here, will work for any pendulum, because the most common thing here is that y'all zone out, which you probably have done by now. And you start to do homework problems and you look through your book and you're like, well, which equation for omega do I use for this? And so we're going to get you to where you're comfortable identifying that it doesn't matter which equation. If you just use the generic one, you'll always get to the same answer. So what I want you to do in your breakout rooms, then I'm going to give you 10 minutes to do this, is I want you to identify the torque involved in this, and then see how you can get to defining omega using torque and forces. So think in terms of what forces we have for torque on this bar that's swinging. And how can I now pull that together to somehow get to omega? So I'm going to give you 10 minutes to chew on this. Does everybody understand what I want you to do? So who wants to volunteer what your group came up with? What'd you come up with for torque?
Just initially, we got LMG sine theta over 2.
LMG sine theta. So where's the over 2 coming from?
Because your the radius at which the force is applied is going to be at the mg sine theta, which is going to be the center of mass of that bar. It's
Perfect.
going to be L over 2.
Cool. I'm going to do this in capital L.
Yeah, we were actually arguing as to what the L in the inertia equation actually was. If it was an L or if it was a loopy boy.
If it was an L or if it was a what?
Some fancy looking loop.
That's my attempt at not doing everything in all cap letters.
It's all good.
So it's supposed to be a small L. Sorry. Okay, so we know that the torque is the force of gravity acting at the center of mass on this thing, and then we have this sine theta. So now kind of going back to our last exam that y'all just finished, I saw several questions posted about, well, how do we solve for this thing if we don't know the angle it's applied? And the hint I gave was, how do I define torque without an angle? There's two different definitions we have for it. And here's my hint to you if you're all like, wait, what? Is that force net equals what? We just said that a few minutes ago. In general.
MA.
Yeah. Yeah. So just like I took you in rotational momentum, where we said like M1V1 equals M2V2, or however you want to do that. How do we translate that into rotational momentum, angular momentum? What did M become?
I,
Yeah, cool. And V?
omega.
Oh my god.
Yep. Yep. So can I do the same thing for force here? What's mass going to be?
I.
Yep. And
alpha?
A? Yep. There we go. So now we have two definitions for torque. Let's see. I can rewrite this because I know that the goal here is this d squared by dt squared gives me acceleration. Remember, the second derivative of position or theta or anything is going to take us from position, however that's defined, to acceleration. So if I rewrite this to be torque over inertia equals alpha, then I feel like I'm getting closer to being able to apply that. So I can rewrite this then, inserting our definition of torque as being L over 2. So L mg sine theta divided by 2 times the inertia equals alpha. And now the only thing I haven't done here is I left off a little negative sign for saying that down is negative. So that's the only thing I'm missing there. It's no big deal.
So can I have a quick question?
Yeah.
Can you just go over how we got torque equal to L over 2 mg sine theta? I didn't quite follow that.
Okay, so what force is making this thing go? What's going to keep it swinging?
The force of gravity?
Yep, yeah. And if I have no friction in there, then all I have is the force due to gravity. And remember, just like, I should do a different color here, just like the material we just finished covering, the force due to gravity is going to act on the center of the mass of whatever thing we're looking at. So if this is a evenly distributed mass over length L, then the force of gravity is acting at L over 2. And
Okay.
then remember, torque in general terms is like FR sine theta.
Right. Okay.
Are we good?
Yeah, I think so. And so the cosine component would be the force that's opposing tension, or do we need that? Is that
Yeah,
what?
so that wouldn't be, so remember what the whole reason we do the sine is
Mhm.
for the torque, we're looking for the perpendicular component.
Yeah. Okay.
I'm not doing a full sum of forces. I'm only looking for the perpendicular piece that's going to keep this thing rotating or pivoting.
Okay.
Are we good?
Hmm.
Okay. Okay. So then let's see. dx dt, another way to look at this is indeed alpha, because it's just acceleration. And if I'm doing it in terms of theta, then I'm looking at a radian change per second. So I can go negative c theta equals negative lmg sine theta over 2 times inertia. Now what I'm going to do is I'm going to say, let's just, for simplicity's sake, to keep this thing generic, is I'm going to say, let's let L, capital L, be, or L over 2, I'm sorry, be the script L, because I just want to clean this expression up just a little bit to make it more generic. So all that's saying is that's the center of mass is what that script L is. All right, now there was one equation video I had you watch in reference to small angle approximations. Does anybody remember what like the name of the game was from that?
Yeah, for a really small theta, sine theta is about equal to theta.
Perfect. Yep. So we say, like, generally, if theta is less than, and this is just a rough rule of thumb, less than about 10 degrees, we call that a small theta. And so then theta equals sine theta. It's an approximation, but it's a pretty darn close approximation. So for our pendulums, what you'll see is they generally don't oscillate too much greater than that 10 degrees. They tend to stay within our small angle approximation. So that lets us to see the negative signs are going to cancel out. So I'll have c theta. I can rewrite sine theta as just theta, and g theta over I. So my thetas cancel.
See one more time.
C is just a generic. Remember, if I integrate, how you end up with, like, C is your generic constant. So C
Yeah.
is anything physical. And actually, we're going to come right to that right now. That's my next step, is to say, what the heck is C? mg over I. So let's take a look at what C is. When we did that, when we did all of this work before, we came up with this coefficient in front of that trig function. So that C, then, you can think of it as being like your A omega squared. The only difference is here, we're just going to think of it in terms of the physical quantity that we actually know. So instead of worrying about the A being there, we're just looking at the omega. So C here is just some constant, is roughly defined as omega squared. And that comes because it's the coefficient in front of this. Or if you're uncomfortable as to why that canceled out or didn't cancel out, why we did away with the amplitude, if you remember, in this step, our A went away and omega was the only thing that stayed. So is everybody good with that step? Nobody's panicking here? Okay. So this omega squared equals L, where L is the center of mass of the system divided by I. Cool. Now, let's see, I've defined I as ml squared over 3 for, that's just the inertia for a bar. So I can put that in there. So I can go L mg over ml squared. And what's going to happen here, that 3 is going to pop up top. And for here, remember, what is I? What is the distance I there? Remember, let me rewrite rephrase that in a different color. If I say mr squared for I, what is this r?
Oh, that would be the length of the pendulum.
Close, close.
Distance from pivot point.
Bingo. Yep, yep. So my distance from my pivot point on this thing is, let's see, is the center of mass to the pivot point. So here it's the exact same that we came up with for the center of mass acting on this force, this L over 2. So this distance here is script L. So my R, as I've done here, is script L. Is everybody good with that? Okay. So let's see, I can look at this, my masses cancel. And that cancels, and so do I end up with, whoops, forgot to cancel that. So for this omega, for this kind of rod swinging back and forth, I get 3 times gravity divided by L. That defines only what's going on here. That's if I have a rod and it's swinging and it's an idealized circumstance. There's no friction, nothing draining energy out of that oscillation. The other one that you see, whoops. I didn't erase everything from the earlier class, sorry. Is this idealized pendulum. And that one, we do the same trick where we're like, it's a massless rod. If it's a massless rod, then the only mass that's making it go is this mass here. And I can do this exact same process. And what I end up with is that omega for this idealized thing is just the square root of G over L. And where does that come from? That comes from the fact that, remember, for a point mass, our inertia is just mr squared. So that 3 goes away. It was never in there. So that's two equations that you have for omega in your textbook. And the reason why we're going through this is because the most common question I get is what's that letter D or L when we have all these distances involved. So being able to pull these things together is going to save you a lot of time and frustration. In fact, now let's think about this as not a massless rod. So if the rod has mass and the ball has mass, now I can come back to our very generic definition of omega. Without canceling anything out, I'm going to have this generic term of omega that I'm going to have, let's see, L is the center of mass of the system. I'm going to make it capital M because it's going to be the sum of all masses. And then the acceleration due to gravity divided by inertia. So if I have more than one mass, I have more than one inertia. How do I solve for what inertia is? So everybody remember from the exam question, the 2 masses stuck together. How'd you figure out the inertia of the system?
You sum them together.
Yep, which is the writing I accidentally still have here. So the I here then is just going to be the sum of all of my inertias. And remember, when this whole quarter started, we started off with this thing called center of mass. So you know how to do that. That's this L. That's center of mass. Oops, center. So center of mass for this thing would be like summing my masses. And if I make this my pivot point here, then it's just the distance everything is from wherever I've chosen my axes to be. And remember, with that one, I can make the axes to be wherever I want it to be. So pick something easy for you, and then go ahead and do your calculation for your center of mass. And when you want to do your center of mass, don't do something at an angle. Just have it like hanging straight down. So you're not overly complicating things. So you'll have like, remember what center of mass. Do I need to remind you all what center of mass is?
Quickly, sure.
Quickly, sure. Okay. So just to remind ourselves, center of mass is defined as, let's see, we'd have like mass 1 times x1, where x1 is away from our whatever axes we've chosen, plus mass 2 times x2 plus mass n times xn. And that goes on forever, divided by the sum of all our masses. That gives us the position for our center of mass. This gives me L. So I can use this, I can solve for where my center of mass location is. My inertias, I just look those up and I can solve those to figure out what the sum of my inertia is of my system. And I can put that into my omega. This thing here answers every question you could possibly have, regardless of the geometry that I'm looking at. And so my suggestion to you is, instead of trying to find an omega that fits every physical circumstance, is just take confidence in using what you know as far as center of a mass and inertia, because you've now done those enough, hopefully, that it's not going to be quite so intimidating. And why are we doing all that? Because now I can answer any question. I can answer what the amplitude is going to be of my oscillation. I can answer what the period is going to be of that oscillation, the frequency. Because remember, omega is, let's see, this frequency has a 1 over s, and omega is radians per second. So the 2 pi makes that radians per second. So I can jump from omega to frequency. In lab, you're going to measure the period and convert that to frequency. And what you're going to do with that piece of information is come back here and relate it to your spring constant. Oh, I erased it all, so that's not helpful. But you can relate it then to your spring constant, because remember, what did we come up with? We said that omega is the square root of k over m. So a little bit of math and substitutions for the period that you measure, you can get to omega. You'll know what your mass is, and then you can solve for what k is. So it becomes pretty handy for being able to solve different kinds of systems. And more importantly, we're going to apply this to things that are a lot more fun than just a swinging pendulum. Because this, moving into next week, is now going to bring us into moving waves and how they oscillate. And we're going to see this kind of repeated pattern for how we can treat our equations of motion. That's what launches us forward into looking at light and some really exciting things. Any questions on that? Let's stop recording. Yes.